I start to get to know the students, and then we just small talk, and then I feel like it's weird to have our small talk recorded. And then students don't want to say anything in the office hour. But anyway, sometimes it's helpful. So we went over a bunch of 1.4 trig limit questions a few minutes ago. So if you had a question on your homework, we went over number 11. I know if you like just got here, this is all a bit much for you. If you would like, stick around after class and I'll put this back up for a few minutes, or I don't mind, I can scan it and email it out if students wanted to see this. We went over number 9. Yours might have been different. I think this was the book variation. Some of these numbers iterate. We went over number 10. I got a ton of email questions on number 10, not a ton, but at least 5. So for number 10, we divided each term by sine theta, and then we simplified. The suggestions that I offered between numbers 9 and 10 were for number 9. If you're not sure what to do, whenever your denominator is just one term, you have this monomial here, it's a good idea to split up your fraction so that each term in your numerator is divided by that denominator. Now, you cannot do that with something like number 10, because in number 10, you have 2 terms in your denominator, not 1. So you can't split this fraction up. You can't just like split the denominator up like that. Remember, we have to have a common denominator to add and subtract. So for something like number 10, it's not super obvious, but a technique I used in class was to divide each term by a quantity. In class, we divided by theta or x, I think it was x. And then for this problem, we divided by sine theta. Now, it's not necessarily the case that this is the only way to do it. This is the most straightforward way. And a lot of times I end up putting a question on the test, and I'll have like a rubric printed out for, you know, like if I'll have my solution process, and then it'll be like, okay, well, they get 2 points for doing this, 1 point for doing that. And then it'll get totally blown out of the water because some students will decide to do it a completely different way. Sometimes it takes up fewer steps, and then other times it takes more steps. So I kind of have to adjust the way that I'm going to grade it, just because for something like this, there's really not necessarily one clear-cut way of doing it. Whereas for other things, there is a clear-cut way. Morgan, yes, what's your question?
So on the email, it said we can use our notes. We can use our notes and the like the trig guide, right?
Yes, yes. You can use your notes. You can use your trig cheat sheet. And your notes include the pre-calc review. I know I said I'm not actually testing you on anything specifically that's pre-calc, but I mean, if any of those topics come up, you're more than welcome to use that pre-calc review. It is part of your notes. So yeah, you can use the trig cheat sheet. You can use your notes. Is there anything else that you might want to use that you have a question about? I think someone had asked me an email question too. Let's see. Oh, someone's asking a question in the chat, and I'm actually seeing it. Can I use the Texas TI-36X? Oh, your TI-83 is broken. I'm really sorry to hear that. Mine is also broken. Yeah, you can use a scientific calculator. That's fine. What I don't want to see is like TI-89 or something, or any sort of CAS, because those do the work for you. So you'd have to actually show me your work. It's hard to enforce that online. But yeah, if there was, yeah, let's just, you can't use it. It's hard for me to enforce. Make sure you're showing me all your work. But for the TI-36X, yeah, any scientific calculator is fine. It's going to be really helpful for you to have a graphing calculator. It's going to be harder to do some of the tabular problems without it, but it can be done. Does that answer your question, Wayne? Okay. Someone had asked me over email. Looking at it now, it's Victoria. Yes. Okay. So some people take notes on their iPads. I know some students have tablets that they write on, and when they take their notes, they just kind of do everything electronically and save it that way. that's fine. So if you have your notes on your iPad and you're using that to go through on your test, yeah, that'd be totally fine. Okay, 1 second. Are we allowed to use Microsoft Lens to scan our work? However you want to scan your work is fine. I just recommend Genius Scan just because I find it to be very intuitive. I like using it. It's just what I've been using for a long time. You don't have to use that. I have had students scan their work in so many different ways. As long as you scan it and it's all together in one PDF file, it can, you know, obviously the PDF file is going to have multiple pages in it, but then that's fine. And Isabella, yes, you may use your textbook. Yes, you may use, it's technically open book, open note. I know this is just what we have to do when we're online. Eventually I'll be back in person and you'll take tests the old fashioned way with a note card and a trig sheet. But I do, in class even, I tell students they can use their trig sheets and a note card. Just at home, you have more resources available to you. And that's just the way it is. Google Drive has an option to take pictures and turn them into a PDF. Interesting. I did not know that, and I've never used it before, but interesting. Yeah, that's fine. However you need to do that is up to you. But just make sure you have it figured out before your test. I had a student last semester and I was so annoyed because he was using a traditional scanner, which is fine. I mean, that's great. Like nobody uses a traditional scanner, but that's fine. And he didn't actually figure out how to use it beforehand. So he's like piddling around over there for like 20 additional minutes and I'm emailing him just like, okay, like your test is clearly late. You're losing 20 points. What's happening? And he's like, oh, we're trying to get the scanner to work. If you don't know how to use your scanner, come up with another option or figure it out now because you're going to lose points the longer it takes you to upload it. And that's the last thing you want is to lose points over something silly like that when you've worked so hard studying for your test and now all of a sudden you don't know how to upload it. And the thing is he left the room so I couldn't even see what he was doing for like 20 minutes. He was supposed to have it submitted and then when I looked it wasn't even there. It's terrible. I had another student though, I don't remember if I mentioned this to you guys. He had logged in from his phone. He had a really great side view with his phone and it was sitting there and I was watching him take the test and then his phone died. And he didn't double check to make sure that he was still logged in. So that is a huge problem because I can't just let you take your exam unproctored and then expect everybody else to be proctored. You have to abide by the same rules as everybody else. So please make sure that if you're on some sort of separate device, either it's plugged in, make sure it's actually plugged in and charging. We have some chargers in this house that we plug them in and we realize like nothing's charging and we gotta plug it in again. Just you know, be vigilant. Yes, Morgan, did you have another question?
Yeah, so do we log in on this Google Meet on our laptops and on our phones as well?
You don't have to log in from both places. I've had students who have really great setups with just one login. Most people log in from just one device. So a lot of times they'll have something set up off to the side so that I can see them. It's close enough that I can see you and see your work. It can't be like across the room on the other side of the room so that I can't see what you're doing. I mean, the whole point is I need to proctor you. But as long as you have it set up so that I can see your paper, at least the side view of your face and 2/4 of your screen, that's totally fine. If you can't get it set up that way, what I found that a lot of students will have their phone kind of like behind them and I can see their screen and I can see their paper, but then I can't see their face. And that's when usually they're sitting in front of their computer and they'll log in through their computer so that I can see their face and then I can see kind of what they're writing, but then I can also see behind them and I can see their papers and I can see their screen. So it kind of depends on the angle and everybody's got a different space that they're dealing with. So for some of us, it's harder to get that angle than others. And depending on what device you're using, it might be harder, versus webcam versus phone. I know sometimes with a phone, it's hard to get an angle. I took out the part about putting your phone in a coffee mug. Teachers suggested that to me. And then every time I put that in my suggestions, students are like, yeah, I tried the coffee mug thing and it just would not work. So if you want to try to set your phone in a coffee mug or some sort of cylindrical container, that's fine. But for the most part, if you do that, you're also going to get a vertical view. And then I really can't see much from a vertical view. I'm going to ask you to switch it to some sort of landscape horizontal view so that I can actually see what's going on. And then you're less likely to need 2 viewing angles. Other questions? Because I have a little bit of a shorter class prepared for you today, just because we only have to finish 1-5. I mean, it'll probably take an hour, but I wanted to give you a little bit of extra time away from class to devote to getting ready for your exam and making sure that your exam space was ready, stuff like that. So I'm not going to keep you till 8:20 tonight.
I actually have a question real quick.
Yes, sure.
Is it all right if we like show up 10 minutes before the actual test and so that way you can view our like area?
Yes, that's a great question. I would love for you to show up 10 minutes early because it is really helpful, because otherwise, if you don't log on till 6, then it takes me a while to get everybody going and checking workspaces. And I don't want to end up having you start your exam late just because it's taking me a while to get through everybody, especially with 28 students. I mean, the thing is, usually the class kind of dwindles down. You know, people drop here and there, and then by the end of class, it takes like no time at all, and you guys start to get your viewing angles down, and it's not a big deal, and then there are fewer of you. But the first test especially takes a while to check 28 people and get everybody going. So yeah, I would strongly suggest you sign on 10 minutes early. And what I do is when you come on early and then I check your workspace, I start an email and then I just start adding people to the email. And then at 6 o'clock, I'll just send the email to that first batch of people for whoever I've checked. I don't think I included this in the email, but some of you don't have pictures on your ECC page, so you're gonna need your IDs. If you want, I can, some of you, I feel like I already know what you look like because you have your cameras on. A couple of you that I'm looking at, but you might want to check your Access ECC. And I know that ECC has been closed, so if you're newer to ECC, you might not have been able to go in and have your photo taken. But otherwise, I can't really verify who you are. So if I don't have a photo for you, it's fine. You don't have to have one uploaded or anything. Just make sure that you have an ID prepared. And maybe I'll make a sticky note to myself to send email to those who I'll need IDs for. I mean, really, you should have your ID ready anyway, just especially in case you look different from your ECC photo, because it has been a while since some of you have had those taken. Oh, and then the other thing I was going to say, which was a little more specific about the homework. If you were in the office hour, I already said this once. When I put together the homework assignment for 1-4, I originally had questions on it about continuity. There were, I think, 3 or 4 of them. I ended up deciding at the last minute when I was going through 1-4 not to cover continuity, just because I felt like we had already talked so much about it, and I was kind of feeling like you guys were a little bit done with that as far as what we needed to do was concerned. And it wasn't a huge deal for me in 1.4. So I took those questions. I have a distinct memory of taking those questions off the assignment. I don't know if I didn't click save or what happened, but they ended up on the assignment. And I didn't realize that until I got a flood of email questions last night, like way more than I would have expected, being like, I don't know how to do this problem. Can you tell me where to start? What's with this continuity? So what I normally would do in that instance is just like make the homework out of fewer points and then just give you whatever score you got. And then you might have gotten some extra points for whatever you did. But for whatever reason, I just said, okay, I don't want everyone to be confused. And I removed them from the assignment. So if you were confused on 1.4 about continuity, I didn't cover it in class. If I don't cover it in class, it won't be on your exam. So don't worry about it. If you had asked me a question on WebAssign, and I went ahead and removed them, it didn't give me the option to respond back to you. I think you would have logged into your WebAssign that would have just said, this question has been removed. And I wanted to actually say something back to you about like, sorry, I didn't mean to include this on the assignment, but then there was no option to reply back. I struggle sometimes with communicating too much in this class. I don't want to overwhelm you with emails. I don't want to feel like you're just getting these emails all the time. But that was probably a situation where I should have sent an email just to be clear. So that you know, in case you were one of those people who encountered that issue on the 1.4 homework, I'm very sorry. I'm not really sure how those problems slipped through. I don't know. I must not have clicked save. Sometimes WebAssign is not the most intuitive, interactive experience on my end. All right. Would it be okay if I use my driver's license to show as an ID? Yes, driver's license is totally fine. It doesn't have to be a school ID. I know a lot of us don't have them right now. And if you don't have a school picture on Access ECC, then you probably don't have a school ID either. Is our computer screen going to show the PDF of the test, or are we supposed to write our answers in some Google form? So it depends. I mean, you're gonna pull up the PDF of your test from your email, and it's up to you at that point if you're gonna, I mean, if you're one of those people who works on an iPad or however you do that on your tablet. I don't know how, some people are just gonna write directly on the PDF on their tablet and submit it. Probably like 1 out of 28 students will do that though. If you have a printer at home, print the PDF, write your work on the printed PDF, upload your pictures and submit. I'm going to have a submissions folder. It's going to be in the assignments tab on D2L, and it's going to say test 1. If you don't have a printer, no big deal. Just use blank paper and start out, with your test and say number 1, and then just write the work. You don't have to rewrite the question. You can just write the work for the problem. But please go in order. If it's like number 1, number 7, number 15, number 3, it's going to be really hard for me to grade. And don't email me your work. Everything gets submitted through D2L, and then your actual tests will be linked to the grade book. So I'll grade it in D2L virtually, and then you'll be able to see, you'll be able to click on your grade book and then see the test from there. So everything gets linked. So don't be like, I have no idea where to upload this. I'll just email it to her. It'll be fine. No, upload it to D2L. It's gonna be under the assignments tab. I put that in the email, but it'll say test 1. So yeah, don't email it to me. Not the same thing. Okay, does that answer your question, Isabella? Okay. I had a student last semester in Calc 2. He actually had a printer at home, but for some reason he didn't start printing out his tests until the last test. And then when he did, he submitted it with a note that said like, wow, this was so much easier when I printed out the test. I wish I would have done that all along. I don't know why he didn't do it all along, but it is a lot easier if you do have a printer to print out your test. I know not all of us do, and that's okay. I have friends who come to my house just to use my printer for things. It's weird. But a lot of people don't have printers or CD drives. It's true. Not that you need a CD drive for this class. All right. Any other questions before we proceed? Yeah, everything comes at us so quickly in the summer.
I wanted to ask how many questions are going to be on the test. I don't know if you answered this question before, but
Someone asked me last time, and I think I said somewhere around 15.
oh, 15. Okay.
I think I said that. I haven't actually written it yet. I mean, I wrote a little bit of it this morning, but I'm probably just going to write it tonight. I usually write it the night before because it gives me, I don't know, I feel like I don't ever want to finish the test until I feel like we've covered everything. I don't know why. I just feel like I get a sense for where we are, and then I kind of base everything I do off of that. So yeah, I'll write it tonight.
Okay. Thank you.
Welcome. But yeah, I think it's like 15. I don't remember. I'm looking for a similar one. Yeah, it'll probably be somewhere around there. Okay. Other questions? Okay, so like I said, I'm not going to cover a ton tonight. I don't want to overwhelm you before your exam. I'm going to finish out 1.5. That's my plan for tonight. It might take me an hour to do, but who knows? It could take a little more than an hour. I don't know. We'll see. But I want to finish out 1.5. And I mean, if you want, we can vote on it. But I kind of feel like I should stop it there and then just have 2-1, 2-2 asynchronous. 2-1 and 2-2 really go together. They're a lot, in some books, they're one section. In this book, they're split into two. They are two shorter sections, and they're sections we don't put a ton of emphasis on. So yes, you will be expected to know the concepts for your exam, but most of what you're gonna, not this exam, the next exam, most of what you need to know for chapter 2 is going to be derivative rules, which we're going to start next week on 2-3. So I feel pretty comfortable saying that you should be good with doing 2-1, 2-2 asynchronously. And I think that would be better than trying to start that tonight and then having you test on chapter 1 tomorrow. It might be a little overwhelming. So unless anyone has any major complaints about that, I think we'll just do that. I don't know what I'm expecting here, that someone's going to pop up and be like, not okay. I don't know. I think you'll be good though. 2-1, 2-2, like I said, they go together. I usually teach them together. So the only reason I would start 2-1 tonight would be just to give you, just because we had the time to do it. That would be the only reason. But I'd much rather you spend that time making sure you're ready for your exam, making sure you have your viewing angle set up, making sure you have your printer working if you plan to use it, stuff like that. Making sure you have an ID, all kinds of things that you need to do to prepare for your exam. Practicing your Genius scan, and of course, going through your homework for 1.5, because the homework that I assign after class today technically won't be due until Friday, even though your exam is Thursday, tomorrow. So you don't technically have to do the 1.5 homework before your exam, but I would strongly suggest it because you want to be prepared for your exam. So that's another reason I kind of want to make sure that we don't spend all night sitting in here doing other stuff we don't have to do for tomorrow. Because I want you to be able to get a good head start on that homework so you feel prepared for your test tomorrow. Okay. I think I'm ready to get into 1.5. Does anybody have anything else that they would like to ask before I do so? I'm going to close my chat box and I'm going to look for the blue dot. It used to be the case that if I closed it, it would beep, but it doesn't do that anymore. Just have to look for the blue dot. It would be helpful if it was even a red dot, but it's not. Okay, so last time we were talking about 1.5 and what we covered so far. Remember this section was actually called infinite limits, limits at infinity, and asymptotes. So the part that we covered last time was the part about infinite limits. So we talked about what happens when your limit is infinity, and we talked very briefly about limits at infinity. So infinite limits would be something like what we saw for A and B. We took a limit, we got the quantity or the value of the limit to be approaching positive or negative infinity. Now, limits at infinity would be a situation where you're taking the limit as x approaches plus or minus infinity. So whereas these would be representative more of vertical asymptotes, if you want to think about it that way, limits at infinity would be more representative of a horizontal asymptote. And then we briefly discussed vertical and horizontal asymptotes. That's the other piece of this section. So you kind of have already seen everything, but we're going to go into some depth today about finding limits at infinity. And some of this will be review from algebra, because you spend a lot of time in algebra talking about horizontal asymptotes. Maybe not a lot of time, but you did spend a decent amount of time talking about horizontal asymptotes. And that's really what limits at infinity are. You're just writing them out a little bit differently. So we're going to talk about that. Now, last time I left off giving you some definitions here for these limits. And I want to remind you of what they are because we're going to be using these today. And I'm actually going to put this up here so we can refer back to it when needed. So the limits at infinity represented n behavior. We wrote these down. We didn't really talk about them. We talked about the fact that if we have a limit as x is approaching positive infinity, and we're looking at x to the nth power, then the limit will be infinity. So you're taking infinity to the nth power, and then your quantity is just going to be infinity. Now, this is for the case that n is a positive integer. So we're not looking at some situation where you have a negative exponent where x is being bumped into the denominator. Now, if n is positive and even, and we're approaching negative infinity, then your limit will also be infinity. But if you're approaching negative infinity and n is positive and odd, then the limit of x to the n as x approaches negative infinity will be negative infinity. Now, I briefly just mentioned, like if n was 2, for instance, you would have x squared, and we have x squared being this parabola. Either way, you have something like this occurring, whether it's x squared, x to the 4th, x to the 6th. When x is getting larger, y is also getting larger. And when x is getting smaller, y is still getting large. So on both ends of this graph, y is heading up towards infinity. Now, that's going to change when you have n being odd. So x to the 3rd, x to the 5th, x to the 7th, those all follow a form that looks more like this, like a cubic function. And you can see in this case that as x gets large, y gets large. But as x gets increasingly small and I head over to the left, then y gets increasingly small. And that's where you end up seeing the difference here in this limit as x approaches negative infinity. So for both graphs, as x gets large, y gets large. But the difference is what happens when x gets increasingly small. For even n, your values head towards positive infinity, and for odd n, your values head towards negative infinity. So that's the big difference there. The other thing that we ended with last time was we talked about this instance where it's possible that you could have had x in the denominator. So what's happening here is k is some constant, and you're taking x to the p in the denominator, and we ended up getting these limits that were infinity, whether x approached positive or negative infinity. So if you want to think about it as you're taking some finite value in the numerator, some constant k, and you're dividing it by some value infinity to the p is positive. So you're taking some finite value and you're dividing it by a quantity that's much, much, much larger than that. And at some point, as this quantity in the denominator continues to get large, the value in the numerator stays the same. Your ratio will eventually head off to 0. And that's going to happen whether x gets increasingly large or increasingly small. Either way, the ratio is going to get increasingly small in this case. So that's the thing that we left off on last time. Now, just to sort of give you a simpler variation of that last piece that I gave you, we can also summarize this one as the limit as x approaches infinity of 1 over x equals 0. And the limit as x approaches negative infinity of 1 over x is also 0. So this is just a specialized form of this last property that I gave you. You're taking a finite quantity and you're dividing it by a quantity that gets increasingly large. Thinking about the value there. And of course, you remember this 1 over x is your reciprocal function, which looks like this. So you're seeing here, x is getting increasingly large, the y values head to 0. X is getting increasingly small, and the y values again head to 0 with these horizontal asymptotes. So this is just a general situation of the previous property. I also want to say something about polynomials. Now, I'll give you the formal definition for the polynomial here. Your book gives it, and it's helpful to see every once in a while. So a polynomial is a function that can be written in this form, a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, and so on and so forth until you get all the way down to your linear term and your constant term. So if you have a polynomial, the limit as x approaches plus or minus infinity of your polynomial p of x is going to be your lead coefficient, a sub n, times the limit as x approaches plus or minus infinity of x to the nth power. You can highlight this and put a box around it if you want to. I'll put a box around mine. I feel like this one, once you start working on these limits, is going to be a little bit more intuitive, but you might want to box it off. Basically, what this limit is stating is that if you have some sort of polynomial, the only term that you're worried about is the leading term of the polynomial. That means the term that has the largest degree. Remember that the degree of a polynomial is just the largest exponent that you see on any term. So this would be an nth degree polynomial. And of course, n is larger than n minus 1, which is larger than 0, or which is larger than 1, which is larger than 0. So sometimes I'm going to give you a situation, or you might see a situation where your polynomial is not written in descending order, and I'll mention that and we'll rewrite it in descending order. Oh, I heard a beep. David, did you have a question, or was that an accidental typing? Because I actually heard the beep for once. It was an accidental typing. Oh. Okay, that's fine. It's just so random that of all the times I catch the comments, it was that. Okay. So your polynomial is being controlled by x to the highest power. Anything else in that case is going to be less important than what happens in that first term with your highest degree. And then your a sub n, the coefficient, is going to make a huge difference as well, because this is going to control what's happening to your graph on both sides. So I'm going to give you definitely some examples here for polynomials, which I'm going to do next. We will discuss. All right, so this would be example 3. Yes, example 3. Find the polynomial limits in infinity, and then we'll move on to rationals after this, and you'll kind of see how rationals just kind of piggyback off polynomials. I should say find the polynomial limits in infinity. And then I'll give you a couple of examples so you get familiarized with this process. So the first one will be the limit as x approaches infinity of 4x cubed plus 2x squared minus 5x plus 2. Okay, so it's important to recognize when you have a polynomial. In this case, we do have a polynomial. We don't have any variables in any denominators. You don't have any variables being taken to negative powers. You don't have any variables inside radicals. So those are the main things to look for. So this is just 4x cubed, 2x squared, 5x2, all polynomial terms. In order for us to find the limit of a polynomial, we have to make sure it's first written in descending order. That means that we need the exponents to go down as we head from left to right. In this case, that's occurring because we have x cubed, x squared, x to the first, and then x to the 0 is just 1. Any quantity to any real number to the 0 is 1, and we're expecting x to be a real number. So we do indeed have this in descending order. So what we're going to do is we're going to take the lead term, and we're only going to focus on finding the limit here, because whatever is happening with this lead term is going to control what's happening with the whole rest of the polynomial. And that's what this theorem up here is telling us, that the limit for our polynomial, whether x is approaching plus or minus infinity, is just going to be the lead coefficient times that limit of x to the nth term. So we're going to rewrite this as the limit. Oh, actually, we have to take that lead coefficient out. I'm always forgetting to move my lead coefficients. The lead coefficient is 4. So that's just whatever your variable is being multiplied by. So we have 4 times the limit as x approaches infinity in our case. And then we're going to take that lead term. The variable piece of that is x cubed. So the 4 goes in front, the x cubed goes in the back. And now you're going to refer back to what you know that you wrote down last time. We are looking at a situation where we're taking the limit as x approaches infinity of x to the n, and in this case, n is odd and it's positive. So whether it's odd or even, as long as it's heading towards positive infinity, doesn't even matter. If we were heading towards negative infinity, we would have to figure out, well, is it even or odd? But in this case, we're heading towards positive infinity. So we're addressing our limit using this piece of the definition. So if n is a positive integer, well, it is. In this case, n is 3. The limit as x approaches infinity of x to the 3rd power is going to be infinity. Now, some of you will look back at this and do your limit that way. For others, this is just going to be a little bit more intuitive. Some students feel very comfortable with saying that infinity cubed is infinity. So some students will just think about this using direct substitution. And they'll say, okay, well, x cubed, we're going to take infinity and cube it. Infinity times infinity is still infinity. If you feel comfortable saying that, fine. 4 times infinity is still infinity. So you just kind of need to get used to working through your infinities here and multiplying infinities by both positive and negative integers. In this case, we're just taking 4 times infinity and getting infinity. So what this means is if you were looking at this polynomial function, if you were to graph it, the y values would head towards infinity as the x values get larger. And you can always check this on your graphing calculator. I'll show you just so you can see it. It's not the hugest deal to me if everybody does this, but I think it's helpful to see. So your polynomial function is 4x cubed plus 2x squared minus 5x plus 2. And when you graph that, I'm going to go back to Zoom Standard because we were probably in some weird trig Zoom last time. You're seeing that as your values of x get larger, so as I move to the right, the values of y are going up. Now, if you're wondering, like, well, how do I know that nothing else is happening, like, over here? How do I know that the graph doesn't go up and head back down again? Well, it's a cubic function. It can have at most 2 turning points. If you remember your algebra, that'll really help you out in this instance. But it's got a turning point here and a turning point there. You're only going to have as many turning points as your degree minus 1. So it's a 3rd degree polynomial. 3 minus 1 is 2. You've got 2 turning points. That's the only thing that can happen with this function. It's already done anything interesting that it was going to do. All it can do now is go up. That's it. So that's what this is saying. As x gets large, y gets large. It's end behavior, which you learned when you learned to graph polynomial functions in college algebra. You can always verify this on your graphing calculator also, but I want to see your work on your test. So on your test, if you just show me this, and then that, and that, that's great. That's all I want to see. But what I don't want to see is you just writing this limit equals infinity. Like, give me some sort of justification for that. And this would be the justification. I want to see some steps here so that you can show me your work. I don't want to know that you just guessed infinity. Show me your work. When in doubt, show me more work. More is always better than not enough. Questions on A? Okay. So we'll do another polynomial. This is the limit as x approaches negative infinity of 4x cubed plus 2x squared minus 5x plus 2. Same function. Now, if you graphed this and you have it in your graphing calculator still, I'm not going to spoil it for you, but if you graphed it and you have it in your calculator, then you have a good idea of what you're expecting to see here. But I'm going to show you this using our properties. So the difference here is that x is approaching negative infinity. So we're heading towards values as far left as we can go versus as far to the right. I'm going to use the same process though. I'm going to take the lead coefficient out. I'm going to multiply this by the limit as x approaches negative infinity of the lead variable term, which is x cubed. You have a couple ways of doing this, but I'm going to go back and look at my properties here. We're looking at the situation where we have x approaching negative infinity. We have an x to the nth here. In this case, n is 3. So if we're heading towards negative infinity, n is positive and odd, then I'm looking at this scenario where if x approaches negative infinity of x to the n, the limit is negative infinity. So I'm going to take 4 times negative infinity. And negative infinity times 4 is still going to be negative infinity. And again, this is something that you can verify on your graphing calculator. I already have the function graphed. And you can see that as x moves over to the left, the y values continually head downward. That's why your limit is negative infinity. The end behavior is that the function values approach negative infinity. Okay, let's do one more. I don't want them to be super straightforward. I'll give you one that's slightly trickier. This is the limit as x approaches infinity of 3x minus 2x squared minus 1. You know what, let's turn this into we'll do both of them. We'll do the plus and the minus version. Because I think it's a good idea. Okay. Now, the big thing I want you to notice here is that your polynomial is not written in descending order. You have 3x to the first minus 2x squared. Minus your constant term. If you're going to take this limit, we're going to have to rewrite your polynomial so that it is in descending order. So we're going to look at both of these limits separately, but we're going to move our terms around so that we have it written in descending order with our greatest exponent first. So the 2 is the largest exponent. Make sure that when you move your terms around, you keep the sign that's in front of that term in front of that term. So this will be negative 2x squared. Then you have positive 3x and a minus 1. So we have to make sure that we rewrite to descending order. So we have not changed the expression. We've just rewritten the order of the terms. Okay, so let's look at these limits separately. First, we'll look at what happens as we approach positive infinity. So negative 2x squared plus 3x minus 1. All right, so I'm going to take the lead coefficient, which in our case is negative 2. I'm going to write it in front of the limit as x approaches infinity. And then I'm going to write x to the n, which in our case is x to the second power. And we're going to look at that limit. Don't rewrite it as negative x squared because you already put the negative on the 2. So we want it just to be x to the n, and anything else goes in front of your limit. Okay, so we're going through this. We're looking at it as far as x is going to positive infinity. We have x to the n. Your expression or is going to go to positive infinity. So you're going to have negative 2 times positive infinity. This one is tricky because it's actually, the limit is not actually going to end up being positive infinity because you're multiplying it by a negative. So the rules that you know for multiplying a negative by a positive and a negative by a negative, those still stand. So positive infinity multiplied by negative 2 is actually going to be negative infinity. And again, you can verify this by graphing it on your calculator. Oh my gosh, I'm just like looking out the window. All these people are at my house and I thought they were at the wrong house, but my husband is such a social butterfly. He's like, these random people are coming over all the time. Ah, yeah. I guess he gets bored. Okay. Does anyone have a question about the limit as it approaches positive infinity? So let's approach negative infinity. Same idea. Move the negative 2 in front of your limit. Send x off to negative infinity for x squared. So everything's the same except this time we're approaching negative infinity. All right, so now the scenario we're looking at here is this one. The limit as x approaches negative infinity of x to the n when n is positive and even. And if that's the case, we're looking at the limit as being infinity. So we have negative 2 times, oh, sorry, we were approaching negative infinity. Oh, yes. No, it is positive and even. Sorry. Never mind. Everything is fine. Negative 2 times positive infinity is, again, negative infinity. So in both cases here, your end behavior is going to be the same on the left as it is on the right. And if you're wondering, well, what would have happened if I had negative 2 times negative infinity? Well, a negative 2 times negative infinity would be positive infinity. So just get, those same rules apply for multiplying a negative by a negative and a negative by a positive, and so on and so forth. And again, you can look at this graphically, but it's a squared function. So you know that both, it's a parabola. You just need to know, does it open up or down? And really, from college algebra, you know that your parabola opens down because your lead coefficient is negative. So it makes sense that you would have the end behavior heading towards negative infinity on both ends. Let's apply this to rational functions. Before I do that, does anyone have a question on the polynomials? So the rationals are super similar. Remember that a rational function is just the quotient of two polynomial functions. All right, so for rational functions, we can call this R of x. Okay, so this is just me writing up officially a polynomial divided by a polynomial. A sub n minus 1 times x to the n minus 1, so on and so forth until we get to a sub 1x and a sub naught. So that just means we have a polynomial in the numerator, and we'll write a polynomial in the denominator, b sub m times x to the mth plus b sub m minus 1 times x to the m minus 1, all the way up to b sub 1x plus b sub naught. So this is a quotient of two polynomials. All right, so your limit as x approaches plus or minus infinity of your rational function r of x is going to be the ratio of the lead coefficients. So a sub n over b sub m times the limit as x approaches plus or minus infinity. And then take the limit of the ratio of the variable terms on your lead coefficients. And then we'll simplify that using exponent rules. So again, anything that comes after this is not having as much power on the function. The only thing that's really affecting your end behavior is going to be what's happening in that first term in both cases. So this is going to be the ratio of the lead coefficients times the limit as x approaches plus or minus infinity of x. And remember your exponent rules. I think I reminded you of this one on the first day. But as long as your base is the same and you're dividing, you subtract the exponents. So it's x to the n minus m. So take the power in the numerator and subtract off the power in the denominator and make that your new exponent. And I'll show you some examples of this, obviously. Now, if you're wondering, like, wait a second, this looks familiar. Didn't we already do this in college algebra with horizontal asymptotes? You did. You didn't officially call them limits. So I'm going to go through 3 examples for you of limits. And then I'm going to remind you of how you did this in college algebra. And if I put rational functions on your test, you will have ample opportunity to check that using what you know from college algebra. Example 4. Find the limits at infinity for r of x. So the first one will be the limit as x approaches infinity of 4x squared minus 5x plus 7 divided by 10x plus x cubed. Now, same idea as with the polynomials. You want to make sure that your polynomials are written in descending order in the numerator and the denominator. In this case, the denominator is not written in descending order, so we'll rewrite it. Now, officially on your test, as long as you show me your work and you use the x cubed instead of the x, that's okay. You don't have to show every little teeny tiny step as long as I can see what you're doing. You just don't want to leave questions in my mind, especially since I don't really know you guys very well, unfortunately. It always makes me sad. All right, so now we've written this in descending order. Once you have done that, we're going to go ahead and use this rule that says that we can take the ratio of the lead coefficients and multiply it by our limit of x to the n minus mth power. So what that's going to look like, I'm going to write it down here, is 4 divided by 1. That's the ratio of the lead coefficients. Now, of course, you can write that as 4. I'm showing you the example, so I want to make sure it's really clear. So I'm just writing mine as 4 over 1 so you can see where everything came from. And whatever you do, don't write it as 4 over 0. This is 1x cubed, not 0x cubed. Otherwise, we wouldn't have an x cubed term. And then, so the 4 is already moved in front, the 1's moved in front, and then you're taking x squared over x cubed. And this is a step you can skip if you'd like. But what I really want to see is that you take x to the 2 minus 3 power. So you're taking your base x to the exponent of the numerator minus the denominator. Now, what you're going to see here is that we're going to end up with another form that I gave you at the beginning of class. So we're looking at 4 times the limit as x approaches infinity. And again, I'm writing more steps than I would really need to see from you. But when I rewrite this again, x to the negative first power is 1 over x. So maybe what I would expect to see on your test is I would want to see this rewrite. If you don't show me the rewrite, at least this would be a good thing for me to see. Because I know for some of you, you're very savvy and you're just like, okay, I don't even need, this is not a step that I would even think to write. I would just skip here. Show me your work. I don't need to see every teeny tiny thing, but I want to make sure I understand your thought process. Then you could maybe go from here to there or something like that. Maybe from here to there. Now I gave you this limit of 1 over x. Remember, you're taking a finite quantity and you're dividing it by a number that gets increasingly large. Well, now we're way behind where that thing was. I'll remind you of what it was. Oh no, there it was. The limit as x approaches infinity or negative infinity of 1 over x is 0. Finite divided by something extremely large. So you would say this is 4 times 0, which is 0. Any questions on A?
Yeah, how did that 1 over x become 0 again?
Oh, so I use this property. It actually came from the k over x to the p, but we had simplified it to this variation.
Oh, okay, okay. Thank you.
So we went directly from here to there, and then we just multiplied it by 4. Other questions? I'm always glad when people ask questions, especially since you guys are virtual. Helps me to kind of figure out where we are, and that I'm not teaching into an abyss. No one likes teaching into an abyss. So let's look at another scenario here. This is the limit as x approaches negative infinity of 5x to the 5th plus 3x squared minus 4x plus 7 divided by 3x to the 5th minus 4x to the 4th plus 5x squared minus 9. Now there's a lot going on here. Normally you'd look at a limit like this and be like, oh my gosh, this looks really crazy. It's not really crazy. That's kind of the nice thing about these is they're really not that crazy. What you're expected to do here is, number one, make sure that your polynomials in the numerator and denominator are written in descending order. Well, in the case for B, I did write them in descending order. We have the fifth power, the second power, the first, the zero. That's great. The fifth, the fourth, the second, the zero. Excellent. So we're already in descending order. Go ahead and take the ratio of your lead coefficients, which is 5/3, and take the limit as x approaches negative infinity of x to the, now this time I'm going to skip right to this part where we take x to the n minus m. So x to the n minus m. So the power in the numerator minus the power in the denominator. That's 5 minus 5. This is really reasonably where I would expect you to go on your test. Now, 5 minus 5 is 0. And remember that any real number to the 0 power is 1. And the limit of a constant is the constant itself. And again, I'm writing a little bit more here than I would expect to see, but I'm the teacher. That's my job. If you went from here to here, that would be okay. Some students like to see more work. Some students like to include more work. The limit in this case is 5/3. Now I'm going to give you one more scenario, and then we're going to go through your algebra rules so you can kind of see how they were different depending on what their degrees were. Before I do one more example for rationals, does anyone have a question on example B? So for C, let's take the limit as x approaches infinity of 4x to the 4th plus 1 divided by 2x squared. And our numerator is written in descending order. Excellent. So go ahead and take out the ratio of the lead coefficients, multiply by the limit as x approaches infinity. Keep your variable to the 4 minus 2. Okay, so we have twice the limit as x approaches infinity of x squared. Now, if you feel really comfortable saying, well, x squared is quadratic, it's just a parabola that opens up. Clearly, the end behavior must be positive in both directions. That's fine. Otherwise, go back to your rules. You are looking at this situation. We're approaching infinity of x to the nth power, where n's a positive integer. Your limit is going to be infinity. Also, if you feel comfortable just saying, well, infinity squared is infinity, that's fine. 2 times infinity is still infinity. Now, I give you 3 examples here. We had 3 very different limits in each case. In the first one, our limit was 0. In the second one, we had a number 5/3. And then in the third one, the limit was infinity. We have 3 cases for horizontal asymptotes for R of x. You learned from college algebra. I'm going to summarize those for you now because I do think that they're very helpful. And if you remember nothing else down the road, I feel like you'll remember these rules. So a limit at infinity is really just talking about end behavior, which is talking about horizontal asymptotes. And the limit is a stronger case because, for instance, if the horizontal asymptote does not exist, you still have to tell me what the value of the limit is. So I'll make sure that we mention that as I go through these cases. But I'm going to relate this back to those 3 examples I just gave you. The first thing that you learned about this in college algebra was that if the degree of the numerator was less than the degree of the denominator, I'm going to abbreviate here. The degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is y equals 0. HA is horizontal asymptote. Now this is for rational functions. Should mention that. Now this would have been A. So when we went over A, I gave you this limit. Sorry, I'm trying to fit everything on here at once. We looked at the situation where we had 4x squared minus 5x plus 7 divided by x cubed plus 10x. The degree of the numerator was less than the degree of the denominator. X squared, or 2, was less than 3 in this case. And if that's the case for a rational function, then your horizontal asymptote is y equals 0. Well, we found that the limit here was 0. So these two go together. The limit 0. The horizontal asymptote is y equals 0. And on your homework, you're going to be asked mostly questions about limits, but occasionally you're going to be asked about a horizontal asymptote. So this case 1 is basically just the same process that we use for example A. It's that same conclusion, I should say. The second situation was that the degree of the numerator equals the degree of the denominator. If that's the case, then your horizontal asymptote is the ratio of your lead coefficients. So y equals a sub n over b sub n. Y is the ratio of the lead coefficients. And that is what we saw for B. So for B, we had a situation where the degrees were the same in the numerator and denominator. In both cases, the degree was 5. So the limit, or the horizontal asymptote, both of those in that case, would be the ratio of the lead coefficients, which is 5/3. Gosh, apparently some children came over. The third case would be if the degree of the numerator is greater than the degree of the denominator. Now, the conclusion here will be about the horizontal asymptote. As far as the limit, you would actually have to tell me the value of the limit. But we would say that the horizontal asymptote does not exist. Now, you can't just tell me the limit doesn't exist. So in this case, you would have to give me more than that. But if I ask you to find the horizontal asymptote, you can use these rules. If I ask you to find the limit, I want you to use the properties that I gave you. In general, whenever you do something on a test, I want you to do it the way we did it in class. But you can check your work using these rules for algebra in case 1 and 2. So if you have those scenarios, then you should be expecting your limits to be 0 or the ratio of the lead coefficients. If they're not, go back and see what happened, because you should be able to expect that these two are going to happen every time. So case C, of course, went along with this one. The degree of the numerator was greater than the degree of the denominator. In that case, the limit was infinity. The horizontal asymptote does not exist. So if the horizontal asymptote does not exist, it could be the case that your limit's infinity, or it might be negative infinity. It could be either one. So that's a case where you definitely would need to supply me more information for the limit. But these are your rules from algebra. You can use them to find horizontal asymptotes, and they correlate well to finding these limits at infinity. Does anybody have a question here? Okay, excuse me, I have to quiet these. I don't know if you guys hear this, but it is like streaming through my consciousness. Hold on. Okay, sorry about that. I think the kid who's over is like 10, and my 4-year-old is like going berserk right now. Okay. I'm going to talk about vertical asymptotes in a minute. While we're talking about limits still, I want to go over one more type of function that you're going to see, and that's the radical function. Before I do that, are there questions here? Okay, so the last kind of function you're going to see is the radical function. Now, I don't want to get too crazy with these. Some of them can be a little bit crazy, but I do want to give you a couple on your homework so you have a chance to work through them. I'll probably put one of these on your exam just because I, want there to be at least some reward for having done these. For some algebraic functions involving a quotient, we find limits at infinity by dividing the numerator and denominator by the highest power of x that appears in the denominator. I'm going to write out here that we're doing this for radical functions. I want to say radical functions in rational functions. I should probably say radicals in rational functions. Say radicals in rational functions. We're going to divide the numerator and denominator by the highest power of x that appears in the denominator. So we're going to divide each term in the numerator and denominator, because remember, whatever we divide the numerator by, we must also divide the denominator by. We're going to divide by the highest power of x that appears in the denominator. Make sure that you're focusing on the highest power of x that you're seeing in the denominator. But I'm going to give you 2 examples of this. In one case, we're going to have the radical in the numerator, and in the other case, we're going to have it in the denominator. You kind of see the difference between the two. These can be tricky. Let me just say evaluate. So this will be the limit as x approaches infinity. And our function in the numerator will be 4x squared plus 9. In the denominator, we'll have the square root of x to the 7th plus 6x squared minus 5. Now, some students are very methodical and they do very well with these because they are so methodical. I'm going to take my function out of the limit to work on this, by the way, because we want to really work on this function before we apply the limit. And I don't want you to feel like you have to keep writing limit, limit, limit over and over again. So let's take the function out for a sec. Okay. Now, looking at that denominator, it looks like the highest power of x is x to the 7th, but be careful because it's only x to the 7th under the radical. Officially, it's not really x to the 7th, but let's focus on what it really is in a second. Focus right now on the denominator. What we're going to do is we're going to write our radical in the denominator, and we're going to divide each term under the radical by x to the 7th. Now, the whole point of doing this is that we want to end up with a situation where we get some of these to either zero out or give us limits that are 0. And you're going to see this at the end when we take the limit. But the highest power we see is x to the 7th. So we're going to divide each term under the radical by x to the 7th. Okay. However, I was saying before, this is not really x to the 7th. When it's under the radical, it is. But if I were to take this out of the radical, I can't divide every term in the numerator by x to the 7th. Otherwise, I'm not dividing by the same quantity in the numerator and the denominator. I want to note to you that the square root of x to the 7th is, of course, not x to the 7th. You learned in algebra how to rewrite these using a rational exponent. So the square root of x to the 7th is actually x to the 7/2 power. Remember, you take the exponent on the function itself inside your radical, and then you divide it by the index. A square root always has an index of 2. So the square root of x to the 7th is x to the 7/2. So under the radical, everything's fine. You can leave it the way it is. But once you divide in the numerator, you can't divide by x to the 7th. Otherwise, you're not dividing by the same thing because you really divided by the square root of x to the 7th. So in the numerator, this is going to look like 4x squared divided by x to the 7/2 plus 9 divided by x to the 7/2. And then we're going to have to go through and simplify this. Now, we just did the hard part. That was the hard part. After this, it's algebra. And then we'll apply the limit, which is a little bit of calculus. But before I proceed here, are there any questions on this part? Okay, let's simplify then. Remember, we have this algebra rule that says that x to the a over x to the b is equal to x to the a minus b. We're going to use that here. So this is a property of exponents. I'm going to have 4 to the x, I'm sorry, 4 times x to the 2 minus 7/2. I'm going to just write this in pieces here. And actually, yeah, we'll leave it like that. The second term, I just want to leave as is, because I actually want it to look like this so that when I take the limit, I'm taking a constant and I'm dividing it by a quantity that gets increasingly large. The only reason I'm rewriting the first term is because there's a variable in the numerator and the denominator, and we want to simplify that so that we just have one variable, not one in each part of the fraction. Now in the denominator, we'll rewrite this as 1, x to the 7th over itself is 1, plus, and then the 6 is going to stay. You can cancel here, x squared divided by x to the 7th. Well, 2 of those are going to go, and you're going to have 5 left in the denominator. If you want to write it like this, you can. If you don't need to, that's fine. And then the last term is already simplified. Now this one's almost done. We're going to do one more simplification on this first term in the numerator, and at that point, we're going to apply the limit. Before I continue, does anybody have a question here? This might be another one of those things where when I do it, it looks so easy. I get that a lot. But that's all right. You will work on these and practice them over the next 24 hours and get good at them. All right, 2 minus 7 halves. Well, you can put that in your calculator if you really want to. 2 is just going to be 4 halves minus 7 is negative 3 halves. So go ahead and subtract, and then you'll have 4, and then x to the positive 3 halves. Plus 9 over x to the 7 halves. And actually, I'm going to pop my limit back on because at this point, we're ready to take the limit. Lord, what's happening with my pencils? Okay, questions there? All right, now you can take the limit. So I gave you a rule a few pages ago. And it looked like this. The limit as x approaches infinity of k over x to the p is 0. We have that situation here. 4 would be k, x to the p. Well, p is greater than 0, and it's a rational number. Check. Same in both of these terms. So what we're going to do is we're going to take the limit of each term separately. So the limit in the first term would be 0. The limit in the second term would be 0. And in the denominator, we have 1 plus another 0 minus 0. And then simplify. And then you're going to feel really dissatisfied because you're thinking like, wow, we just went through all that just for 0. Yes. It's true. I can't deny it. You went through all that just for 0. So the whole point of dividing by the highest power in the denominator is so that we get this situation where we have a bunch of terms where that occurs, and then we end up not having 0 in the denominator because we don't want that. I'm going to do one more of these, and then we'll synthesize all this together in an asymptote example. Any questions here? Oh, I heard a beep. Oh, Victoria, what's your question?
Oh yeah, I just wanted to know if you got the 0 from the last rule of the limits at infinity for the end behavior. Is that where you got the 0 from?
Well, I took it from, was it the last rule? It was the last rule that I gave you last time.
Okay.
Yeah, so this one.
Okay. Okay, that's it.
Yeah, we've kind of used the rule today, but we used it in its more specialized form, which was this one.
Yeah. Okay, cool. Thank you.
Mm-hmm. Okay, other questions on this one? So like I said, the hard part is just figuring out what to divide by in the numerator and denominator. That's it. And it's really just an algebra problem. So we'll do an example B here. Try to keep that there for you. The limit as x approaches infinity of the square root of x to the 5th plus 7x squared divided by 5x squared plus 1. All the better pencils are downstairs. Don't ask me why. Don't know. So once again, we're going to pull this out of the limit to work on it. And we're going to divide by the highest power that we see in the denominator. Well, in the denominator, we have an x squared. Don't worry about 5x squared. The 5 does not matter to us, but we're going to take the denominator and we're going to divide each term by x squared. Now, what we divide by in the numerator, we must also divide by in the denominator. However, if we just took the denominator and divided it by x squared, we can't do that under the radical because then we'd be taking the square root of x squared. So if we did that under the radical, note that the square root of x squared is actually x to the 2/2, which is just x. So we don't want to just divide by x. What we want to do is we want to make sure this quantity is an x squared to match the denominator. So if we're going to do that, then I need to write a ratio here that's going to get me x squared. Now, I can't change the index of the radical. It's a square root. There's nothing I can do about that. So no matter what, I'm going to have x to the something over 2. But if I want it to be x squared, then what gets written over 2 needs to be a 4. That's the only way around that. And then I can rewrite this as the square root of x to the 4th. And that'll be the trickiest part of all of these problems. It's just working with those radicals. And once you get used to doing it, it won't be tricky. Just make sure you do the homework. That's all. There won't be a ton of them, but enough to get you feeling comfortable. So that means that I'm going to divide in the denominator, or I'm sorry, in the numerator. So divide in the numerator under the radical by x to the 4th. Because then I'll be taking the square root of x to the 4th, which is equivalent to saying x squared. So we're going to write our radical. I'm going to write x to the 5th divided by x to the 4th plus 7x squared divided by x to the 4th. All right, any questions there?
Yeah, since you divide by x to the x squared on the denominator, why didn't you also divide that on the numerator?
Yeah, so technically I did. It's just that in the denominator, there was no radical in it, so it just looked like x squared. But in the numerator, remember that the square root of x to the 5th divided by x to the 4th is the square root of x to the 5th divided by the square root of x to the 4th. So we said that the square root of x to the 4th was x squared. So this is really the square root of x to the 5th divided by x squared. The only difference is because we wrote it under a radical, we had to increase the power.
Okay, okay.
Yeah, so I think If you break it down like this, it's easier to see. Go ahead, Renee.
Would you also have to do that again for the denominator? For it to become
Well, in the denominator, I didn't have it in a radical, so I didn't have to correct for anything.
Okay.
So the big difference here is between A and B. For B, I was dividing in the denominator, which didn't have a radical. So I had to correct for that in the numerator and increase the power. Whereas for A, I was dividing under the radical by x to the 7th. And then I had to remember that x to the 7th is not the same as the square root of x to the 7th. So I had to decrease the power when I divided in the numerator. So if you have a situation where your denominator has the radical, when you divide in the numerator, you're going to have to decrease the power. And if you have a situation like B, where your radical is in the numerator, then you're going to have to increase the power in the numerator when you divide it out. Because
Okay.
that radical will force that power down. Does that help?
Yeah, that does.
Okay. I'm trying to write out more of my thoughts here so that it's a little bit, sometimes just writing things in words and then looking at them later, I think is helpful as you kind of go through your homework, look through your notes again. But yeah, essentially everything comes down to that radical and the fact that x to the 4th is not the same as x squared, but the square root of x to the 4th is the same as x squared. There. And that's why these are tricky. Any other questions before I proceed? These awkward silences are weirder online. In class, I would stare at everybody in the face and be like, any questions? And then I would just like look at everybody. Because I got dinged once during an evaluation because I said, does anyone have questions? All right, moving forward. And I like didn't give them enough time to respond. But I can't stare at everybody in the face right now. So I just have to try to give you some time and see if you have any questions. Do the best I can. Here's your expression. We're going to put this back into the limit and simplify. X to the 5th divided by x to the 4th is x. X squared divided by x to the 4th, well, you're going to have 2 factors of x left over in the denominator. And that 7 still stays in the numerator. And in the denominator, we have 5 plus 1 over x squared. And we're going to make repeated use, remember, of your limit, recall, whether it's plus or minus infinity of k over x to the p equals 0. And we're going to take the limit of each term separately. So in the numerator, I'm looking at the square root of, oh, and this is going to be weird too, because you're looking at the square root of infinity plus 0. And that's okay. Divided by 5 plus 0. So we're using like direct substitution here. Just pop that infinity in wherever you see x. For the second term, you're just using this rule. In the denominator, the limit of 5 is 5. And then in the second term, again, you're using this rule of k over x to the p. The square root of infinity is still infinity. Infinity divided by 5 is still infinity. Students always want to argue with me about that. They're like, well, technically, if you take half of infinity, it's not infinity anymore. No, it's still infinity. Whether you take half of it or a fifth of it or a thousandth of it, it's still infinity. I know it's odd. My son keeps trying to tell me that, well, technically there's a number greater than infinity. It's like infinity plus 1. And I'm like, yeah, I know, but it's still infinity. And he's just like, no, not anymore. I'm like, yeah, it is. He's 6, so it's a hard concept for him. Okay. All right, so I'm going to give you a definition of a vertical asymptote, and we will talk about one example where we talk about vertical and horizontal asymptotes and domains and kind of put everything together, and then that's all I have for you tonight. And then you can go study and prepare for your test. Oh, predicted that. Definition of a vertical asymptote. And like I said, vertical asymptotes for most of you guys are going to be pretty intuitive. So this is going to be a non-removable discontinuity where the one-sided limits don't exist. Because remember, if you have a non-removable discontinuity where the one-sided limits exist, then you have a jump scenario. Usually that's going to happen with some sort of piecewise function. The line x equals c is a vertical asymptote of f. Your function, I should say f of x, maybe that'd be better to say. If any of the following is true. One, the limit as x approaches c from the left of f of x equals infinity. The limit as x approaches c from the right of f of x equals infinity. The limit as x approaches c from the left of f of x is negative infinity. Or the limit as x approaches c from the right of f of x is negative infinity. So if any of those are true, then x equals c is going to be a vertical asymptote of your function f of x. Example 6. For r of x equals 4x to the 5th divided by x cubed minus 1. That's a cube. Trying to fix it made it worse. There we go. We're going to do a couple of things. The first thing we're going to do is find the domain. Oops, sorry. Here we go. So technically for something like this, you should factor the denominator. If you don't remember how to factor a difference of cubes, there's a rule for it. But for this one, for the domain, the only real value you're going to come up with is the one that you're going to notice anyway, that x can't be equal to 1, because if 1 cubed is 1, 1 minus 1 is 0. But remember, you do have a rule for the difference of two cubes. It's a minus b times a squared plus ab plus b squared. Oh, there was a rule that somebody told me, and I'd never seen it before. And every time I forget it, some student knows what I'm talking about. It's a rule for the signs. Maybe I'll remember it. If you have a sum of two cubes, it does that. There's something about like, if anyone remembers it, jump in. It's how to remember the signs for these terms. It's like some mnemonic. Oh well. Either way, you might find these useful as you work your way through the course. You might want to have them in your notes. You never know when they could come in handy. Either way, if you were looking for the domain of your function, you could factor your denominator. It would be x minus 1 times x squared plus x plus 1. Using the difference of two cubes. And then clearly you'd be looking for instances where your denominator would be equal to 0. You want to force it to not be 0. We're looking for the domain here, what values of x we can include. So we're going to first focus on what values we cannot include. And generally speaking, with the difference of two cubes, you're not going to be able to solve this one. It's going to be some sort of imaginary value, which in this case it is. You can always try. You could use the quadratic formula. You'd end up in a mess. But we can say that x is not going to be equal to 1. I don't want to leave you hanging there. If you use the quadratic formula, I don't think we've used that all semester, so it's probably good to have it written down. Negative b plus or minus the square root of b squared minus 4ac all divided by 2a. If you were looking for values where this quantity would be equal to 0, well, you wouldn't be able to find them. You'd be looking for, let's see, negative 1 plus or minus the square root of 1 minus 4 times 1 divided by 2 times 1. Notice that the radicand would be negative 3. So in this case, you're not going to have any values of x that would be equal to 0. Or such that your polynomial would be equal to 0, I should say. All right, so you would just have this guy to focus on, and we would say that the domain would include any values from negative infinity up to 1, and then from 1 to infinity. So that answers part A. Questions on A? So for B, we're going to find any horizontal asymptotes. Now, so far, I've only asked you to find limits at infinity. So for limits at infinity, if the horizontal asymptote did not exist, you'd actually have to tell me in that case whether it was positive or negative infinity. However, if I ask you for a horizontal asymptote, you can just tell me the horizontal asymptote does not exist if that's the case. So let's go through here and look at the function. I'm going to rewrite it for you just because it's so high up there now. 4x to the 5th divided by x cubed minus 1. Now, when we're looking for horizontal asymptotes, you don't actually have to set up a limit at infinity if you don't want to. You can, but it's unnecessary. You just need to look at those rules that I talked about for horizontal asymptotes, which had to do with the degrees of the numerator and denominator. And by the way, there's a trick to that. If you want to see it, students always ask me to see it, so I'm gonna show you right now. So you can use the rules from college algebra. If the degree of the numerator is greater than the degree of the denominator, then your horizontal asymptote does not exist. Now, I always forget which one is which. I can never remember. Is it the degree of the numerator being greater than the denominator, or is it the degree of the denominator being greater than the numerator? I can't remember. So what I do is I always use case 2 when I'm looking at horizontal asymptotes. What I do is I create a function just by rewriting my function, and I make the degrees the same. And the way I do that is by creating x to the 5th in the denominator, but I just write it with 0 as a coefficient. So these two functions are exactly the same. This one just has a term 0x to the 5th in the denominator. The reason I did that was because I want their degrees to be equal, because I know that there's a rule that says that if the degree of the numerator and denominator is the same, then the horizontal asymptote is the ratio of the lead coefficients, which in this case would be y equals 4/0, which means I can't divide by 0. My horizontal asymptote does not exist. So that's another trick you could use, regardless of whether your degree in the numerator was greater or smaller. We could have used a reciprocal and we could have done the exact same thing. But you can always use case 2 and make their degrees the same by putting a 0 wherever you need to put it in order to make the degree the same. So that's the horizontal asymptote. You would say it just does not exist. However you want to, if you want to set up a limit at infinity, that's fine. You'd have to look at both plus and minus infinity. But I think these rules are easier if I'm just asking you to find a horizontal asymptote. Does anyone have a question about B? Okay. Now C is find any vertical asymptotes. Now, we already said that 1 was a value that we were excluding from the domain. Therefore, we can say that x equals 1 is a vertical asymptote. And we can only say that because the discontinuity is infinite. X equals 1 would be a vertical asymptote because there's an infinite discontinuity at x equals 1. It's not in the domain, but remember that you can have a value that's excluded from the domain and it could be removable. In this case, it's not. What you want to look out for is a situation where maybe you could cancel that out. So I gave you some examples when I was going over continuity, and there was an instance where you could cancel out a factor and it was like you were getting rid of the discontinuity. In this case, there's nothing to cancel out. You can't simplify it. Your function looks like this. We cannot remove the discontinuity at x equals 1. Sorry, I'm running out of space here. There's no way that we can cancel it out. So because of that, we would say that there's a vertical asymptote there. If we could cancel it out, let's say that you had something like, I don't know, students always want to see examples. X minus 5 divided by x squared minus 25. Yeah, this is similar to the example I gave you for removable discontinuity. Sorry, I'm smashing this in here. Now I have to rewrite it. And if you can do that by factoring and canceling, then you would not have a vertical asymptote at x equals 5. In this case, you would only have a vertical asymptote at x equals -5. So this is just a scenario where you could have a value that's not in the domain. So here the domain would not include plus or minus 5. However, at x equals 5, the discontinuity is removable because we canceled it out. At x equals -5, we couldn't remove it, so you'd have a vertical asymptote there. So I don't want you to think of vertical asymptotes and domain as being synonymous. That's all I had to say about 1.5. You guys do have a test tomorrow, so I don't want to feel like I'm leaving you in the lurch. If you have questions, stick around. I will be on until 8:10. If you don't have questions and you want to go and get to work on your homework, I'm going to post an assignment and be extra careful not to include anything on there that I don't want you to do. But do stick around if you have questions. Like I said, I'm going to stay until 8:10. I just don't want to force you to stay on in case you feel like you would make better use of this extra 20 minutes by actually, doing more work to prepare for your exam. Or eating dinner earlier so that you can do more work sooner to prepare for your exam. Okay, so that's all. I'm done. If you have questions, email me or stick around another 20 minutes. That's fine too. Number 13 on the test review. Yes. Let's see. Okay, so this was using the squeeze theorem. The limit as x approaches 0 of the square root of x cubed plus 2x squared times the sine of 6 over x. Okay, so when we're using the squeeze theorem, let me get back to you over here. There we go. We're going to start with our trig function, and we know that the sine, no matter what the angle is, it has to be between the values of -1 and 1. So start out there, squeeze it between -1 and 1, and then you're going to build this function up. So what you're going to do here is multiply each piece of the inequality by your radical. Like that. And then what I'm going to do is I'm going to take the limit on the left and the right, approaching 0, same as my above limit, and I just need to show that they're the same. And as long as I can show that they're the same, then I can conclude that my middle function must also have that same limit. So I'm going to start with my left side. Then this limit is negative square root 0 cubed plus 2 times 0 squared is negative 0, which is 0. And then do the same thing on the right-hand side. This is one of those limits that is always going to look a lot harder than it is, just because the function looks so crazy. And then you can say that because the left and right limits are equal, then the limit of your function must be the same, the squeezed one. Joseph, what do you think?
So why did we get the negative part of that?
Where did we get the negative? Oh, just from the -1. Oh, you're welcome, Joseph. Yeah, so the negative piece just came from saying that the value of the sine function always oscillates between -1 and +1. And then we just multiplied each piece by this radical. So 1 times the radical gave us this part. The sine of 6 over x gave us the middle, and then -1 times the radical gave us that.
Okay.
Do we have to worry about 6 over x becoming an indeterminate form? No, with the squeeze theorem, you don't need to worry about that. All you need to do is just kind of build it out, and as long as you can prove this with the endpoints, that's all that matters. Yeah, I know it seems weird because it seems like, wait a second, the x is in the denominator. This could be problematic. Don't worry about it. Valid concern. Burfin, did you still have a question about that? Were you unsure?
So you said we multiplied by -1 and +1, but when you were taking the limit, you took the -1, like the negative portion.
Yeah, so I took the limit of the left bound and the right bound. So this one was the left bound and the second one was the right bound.
Oh, okay, so you did both.
Yeah, you have to do both. Otherwise, you have not actually used the whole squeeze theorem.
Okay, thank you.
You're welcome. Sorry, I'm just determining what homework I'm entering. Will the office hour question solutions be uploaded? It would be nice if I could upload them into our calendar. That would be really nice. I don't know if I can do that though. I'm going to look into it. But I can email them to you if you'd like. I don't know if I can actually edit. Maybe I can. Because that would be really nice, wouldn't it? I guess technically I could put them in the same place as I put the YouTube link. Let's see. Edit my event. You'd think you'd be able to attach something. I think I can. Yeah, I'm going to attach them to our Google Calendar. So as long as you have accepted the Google Calendar, which like half the people still have not, which is fine. You don't technically have to, but it's helpful. If you accepted it, I think you have. Yes. So yes, Patricia, you will be good to go. I'll scan it with my Genius Scan and upload it. Put up some homework for you folks.
Also, I have a question.
Yes.
Are you gonna include the vertical asymptote and horizontal asymptote in the test or no?
Yeah, I will. Because it's
But-
all technically review from college algebra. And there's not a whole lot of that. So, I mean, I might not ask about it, but I could.
Okay. Thank you.
You're welcome. Putting up some homework for you right now. I'm still recording. I don't know. I just felt like I didn't know if you guys had a ton of questions. Actually, most of the 1-5 stuff we already did. There's not a whole ton to do here, so it'll be a pretty short assignment. All right, that should be good. I feel like I have to double check these before I put them up here now. Okay. Save.
Also, I wanted to ask, you know how you wanted us to like print it if we could?
Yes.
Are we gonna have time to print?
Yes, you'll have the 15 minutes. You'll technically have until 8:20 to take your test, and then you'll have 15 minutes to do anything else. So technically, whether you use it later, earlier, I mean, it all depends, I guess, on, I mean, my printer, they know it's really fast. So it kind of just depends, I guess, on your setup.
Okay, thank you.
You're welcome. Friday, 6 p.m. schedule. Okay. Your 1-5 homework is up. I'm gonna stop recording. There's not a lot going on here.